Examine the vascular network of a human lung alongside the arms of a growing dendritic snowflake. These two structures have entirely different origins, but they share an identical geometric pattern. They both face the exact same physical problem. They must perform massive amounts of transport within strict volumetric limits. Whether exchanging oxygen and carbon dioxide in blood or dissipating latent heat during a solid phase transition, efficiency is dictated by the surface area to volume ratio. A higher ratio allows mass and heat to move across the boundary at a faster rate. This geometric model shows the mathematical limit of a Euclidean non-fractal shape. For a sphere, the surface area to volume ratio reduces down to 3 divided by the radius. As the radius scales up, the ratio falls along a steep hyperbolic curve. The larger a solid object gets, the less relative surface area it has to interact with its environment. Human survival requires extracting a massive amount of oxygen from the air. To breathe, our lungs need between 50 and 100 square meters of surface area, roughly the size of a tennis court. But that entire surface has to fit inside a chest cavity holding roughly 5 liters of volume. Biological organisms and physical systems cannot infinitely scale their volume. To survive these spatial boundaries, they bypass Euclidean geometry and rely on fractal branching. In mathematics, endless complexity mapped at arbitrarily small scales is generated using recursive functions, categorized as L-systems and prefractals. You start with a single axiom string and apply a set of parallel rewriting rules. With each iteration, the simple line expands into a highly dense network, generating massive surface area without expanding its outer boundary. Biological systems execute this abstract mathematical iteration using genetic expression. In human lungs, DNA codes for exactly 11 orders of branching, terminating at the alveoli. An ice crystal achieves this exact mathematical iteration without DNA, without a central blueprint, and without memory. It is driven purely by thermodynamics. Biology uses coded evolutionary rules. Physical matter relies solely on localized thermodynamic boundary conditions to execute fractal geometry. To map those boundary conditions, we look at the microenvironment of an ice crystal growing from a field of supersaturated water vapor. In fluid dynamics, the ratio of mass transport by diffusion to mass transport by physical growth is measured by the Peclet number. For a growing snow crystal, the Peclet number is roughly 10 to the negative 5th power. This extremely low ratio proves that particle diffusion adjusts the density of the surrounding water vapor almost instantly relative to the physical growth rate of the crystal. Because of this disparity, particle transport operates in a steady state, mapped precisely by Laplace's equation, where the Laplacian of the concentration equals 0. As water molecules arrive at the surface, they are governed by attachment kinetics. These are the physical rules dictating how free-floating molecules incorporate into the solid ice lattice. Attachment kinetics naturally favor stability. Molecules settle into the lowest available energy states, creating flat, low-energy facets. This simulation maps the diffusion lines around a growing ice prism. The supersaturation lines pack tightly at the sharp corners, indicating a higher density of available water molecules. Heat and particle diffusion favor pulling the crystal outward into that dense vapor. The resulting crystal morphology is an ongoing physical compromise between the stabilizing force of surface kinetics and the destabilizing force of diffusion. Stability holds until a facet reaches a specific width, concentrating supersaturation at the edges. A microscopic bump enters this zone, triggering a feedback loop. It gathers mass faster, reaching further into the dense vapor, accelerating growth until the facet collapses, generating a primary branch. This localized morphological anomaly repeats at every new tip. As branches grow wide enough to experience unequal diffusion, they fracture into subbranches ad infinitum. Fractal branching in non-living matter emerges entirely from the Mullins-Sekerka instability, overriding surface attachment kinetics. This Nikaya morphology diagram maps types of snow crystals against temperature and supersaturation. In the lower zones of low supersaturation, kinetics dominate, allowing simple plates and columns to form stably. In the high supersaturation zones, the diffusion instability forces the creation of complex fractal architectures. Temperature modifies the internal attachment kinetics along the horizontal axis. determining whether the instability acts on a flat plate or an elongated column. When a stellar snowflake forms at the limit of high supersaturation, it produces this deeply repetitive structure. The infinite variety of snowflakes is simply water navigating the exact same transport equation under slightly shifting environmental boundary conditions. Biological evolution optimized the human lung to bypass volumetric limits over millions of years. Thermodynamics forced the snowflake to bypass diffusion limits in a matter of seconds. Despite using vastly different mechanisms, DNA versus phase transitions, both systems arrived at the exact same geometric solution. Fractal geometry is the universal mathematical algorithm all matter uses to negotiate boundary limits in a three-dimensional universe.